Hello everyone, my name is Elisa Baum and I am Percona's Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct a bit of house cleaning. First, could you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me. Okay, great. Thank you very much. I see a bunch of hands. That's very good. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we'll take time to answer as many questions as possible. Those that aren't addressed will be answered in a follow-up blog post on Percona's MySQL performance blog. In addition, I will make a recording of this webinar and make sure that everyone here gets a copy within 48 hours. I would like to thank you for attending today's webinar, MySQL Query Patterns Optimized, presented by Bill Karwin, who is Percona's Principal MySQL Instructor. And with that said, I'd like to turn the floor over to Bill. Bill?
Thank you very much, Elisa. This is Bill Karwin, and I'd like to present to you today a presentation that I've been working on called MySQL Query Patterns Optimized. I've been answering questions for a long time, not only for Percona training and consulting, and also in the past on internet forums such as Stack Overflow and the MySQL forums. And I see a lot of query patterns or types of queries that vary from one project to the other, but they have a lot of patterns in common. So I was going to try to identify some of these in this presentation and show you how to measure their performance and how to optimize them. And hopefully this can give you some good insight into your own projects as well. Optimizing SQL queries in MySQL involves identifying the queries, so we need to know which queries are running from our application. You can get that from query logs or from your own source code. But sometimes in the source code, you may not have access to the actual SQL query. You may be using some sort of layer like a ORM or Hibernate or some other layer that's generating the SQL queries for you. So look in the MySQL logs to get the actual SQL. Measuring the optimization can be done with several different commands. We'll show you examples of each of these for the patterns that I'm going to cover. The explain can give you the optimization plan, but there's also ways that you can measure the actual execution time with show session status and show profiles. And then afterwards, making changes to the indexes or even rewriting the query can be necessary to try to improve performance. For the examples in this presentation, I have a toy version of the Internet Movie Database, IMDb. Primarily, it has a table called Title that has movies, television shows, and even video games. And then it has a few other supportive tables. For example, a intersection table called Cast Info that records who is starring in this movie, even crew and directors and so on, that matches the person's name and what role they were performing for the movie. And then on the left is kind type, which is just a lookup table that records whether it's a movie, a television show, or a video game. So that's just to give you some context for the query examples we'll be showing. The query patterns, some of the frequent ones that I see come up on internet sites and in our customer applications that we do audits for at Percona, and fall into these categories: exclusion joins, random selection, greatest per group. That's actually one that's very popular on Stack Overflow. I created a new tag for that, greatest per group, and now it has over 600 questions, everybody asking about variations of that pattern. Dynamic pivot and relational division. Let's talk about exclusion joins first. An example of a problem that you would come up against, the requirements for a given application. In this movie database, for example, say I want to find recent movies that had no director. Maybe there would be a movie that was totally crowdsourced, or maybe the director didn't want his name associated with it. Anyway, we want to find those types of movies in our database. Here's one solution that involves a not exists predicate. In this example, we see that we're querying from the title table to find the movies, restricting it to kind ID equals 1. That's a value from our lookup table that corresponds to movies. And for recent years, we just are limiting it to the range of movies with the production year greater than or equal to 2005. So that's within the last few years. That's sufficient for that requirement. And then the requirement to find those with no director, we want to find that there's no such entry in the cast info table, that is the mapping table to people who worked on the film, where there is a person with a role ID equals 8, and that's just corresponds to the director role for this particular database. This would be an ordinary type of query to see in your application that uses a subquery to try to look that up. But the difficulty with this query is that the subquery is a correlated subquery. That is, because it's restricting the results in the subquery to only those for the particular movie that's being considered in the outer query, it actually has a different result from the subquery for each row of the outer. And therefore, MySQL has to execute that subquery many, many times, as many times as the number of rows that are considered from the outer query. That's the nature of a correlated subquery. How can we measure how this works? Well, when I tried to run this query, you can see in the upper right I have a little stopwatch icon, and I'm going to show in the examples how long it takes to execute these queries. In this case, with the correlated subquery, it took at least 1 hour, and I gave up and interrupted the query at that point. It was taking too long, clearly unacceptable performance. So maybe some indexes will help. The index that I created first was on the title table, that of the outer query. I'm looking up a specific value for the kind ID, so the kind ID 1, and that became the first column of my index. And then once I find those, within the movies subset of those rows, I want to find those with a particular range of production years, and that became the second column of this compound index. A good tip on index design is put all the equality predicate columns first, and then the last column in the index should be the one that has a range predicate. I actually talked about this more in another webinar that I gave a few months ago. Create index MR, and this is the second one on this slide, and that is for the subquery on the cast info table. For each of the movies in the outer query, we'll look up a particular movie ID, so that becomes the first column of the index. And then when those are matched, also consider the role ID to make sure that we're considering only directors. And that is the second column of the index. We can use explain on the query to try to find out how the query optimizer is going to use those indexes. In this case, it first considers the primary table with a range type of access, because we're getting a range of years that counts as range, even though we did equality on the type, like the kind ID. And it considered 189,000 entries, or that's actually an estimate. The number of rows in the explain output is not always precise, but it's within the same order of magnitude. And then the second row here shows that it's executing a dependent subquery once for each row of the outer query. It's making good use of the index that we created for the cast info table, comparing that to the title ID and then the constant value for the director. But it's still executing that many, many times. And if we execute that with the same SQL query with those indexes in place, we see that it's gone down from over an hour, or at least an hour after I interrupted it, down to 4.87 seconds. How can we get that a little bit better? The indexes that we have on this table may be too large for the memory allocation that we have to the index buffer. This is actually a pretty important point about query optimization. That every read query is going to try to read most optimally content from within cached data in the buffer pool. If your buffer pool is not as large or larger than the amount of indexes that you need to store, then every scan of an index may have to do this in batches. It may have to pull in parts of the index into memory and then evict parts of it during the same SQL query, loading other parts into memory, and then do that repeatedly if you're running these queries frequently. In my test here, I had a very small buffer pool size, only 64 megabytes. That's actually lower than the default buffer pool size for MySQL. So this caused a lot of overhead or turnover in my buffer pool as it was loading parts of the index in and evicting other parts. Incurring I/O is something we'd like to avoid during the index scan. I increased the size of the buffer pool to about 2 gigabytes, which was larger than the indexes that I needed to scan, and I got an immediate increase. So just that tuning change, in addition to creating the indexes, got the query down to 1.20 seconds. Another way we can measure the performance of this is by measuring how many rows it actually read. The numbers that were reported by Explain are estimates only, and you can't always rely on them. There also are some inaccuracies from time to time in the output of Explain. So a better thing to do is to use the Explain to guide you on how it's using indexes, but then also measure in different ways. For example, with the show session status like handler. The handler status variables indicate how many times the SQL portion of MySQL has made requests for individual rows of the storage engine. So you can run it like this. You can zero out the counters of how many rows have been read with a flush status, run your SQL query in your test environment, and then show session status like handler %. The session status will ensure that you're only getting the count of row requests for your own session, not those that are happening globally throughout the whole server. And here's an example of the output. All of those different handler prefixed status variables are counts of how many times those individual calls have been made. The handler interface is an API that the MySQL storage independent portion makes requests of the storage engine. And here we see that it was doing a whole bunch of read by index lookups. For example, if it was looking up into the index on the cast info table for that subquery, and it also was doing that to get the first row in the title as it was looking for movies, scanning through that index. And then read next is advancing in index order. That is the queries for the rows in the title after the first row as it was advancing iteratively through that table. Show profile is another means by which we can do timing tests. You can enable this in your session in the MySQL tool. Set profiling equals 1 turns it on, and after that it's actually recording times at a very, very fine degree of detail for each query that you run in that session. It doesn't do profiling for all of the sessions. If you need that, you might want to look at the performance schema, which was covered in a webinar recently by Peter Zaitsev. And those recordings are up online if you want to check that out. But this feature, Show Profile, is just for testing. It's good to enable it in your current session when you're at the MySQL prompt. When it's enabled, then you can run a query. For our example, select title, and then get a report of how long it took in seconds for that query to run. You can run multiple queries too, and it will give you a whole table of them. If you want more detail, you can go into Show Profile for query, and then which of the queries starting from 1 after you enabled the profiling that it would record. Here's an example. In this case, I found that because of my correlated subquery executing that inner query many, many times, it would actually overflow the amount of information that the profiler could display. We'll see some better examples of the profiler displaying more interesting information a little bit later. in this case, we saw it sending data, executing, sending data, executing, sending data, executing many, many times, and those were the iterations of the correlated subqueries. So what other type of solution could we get for this particular problem? There's a not in solution. Instead of not exists, we could use not in. In this case, instead of having a correlated subquery, we just select all of the movie IDs with directors from the cast info table and compare that whole list of directors to the movie ID of the outer query. If this movie ID is not in the list of movies with directors, then it's a movie with no director. Look at the stopwatch. It's executing in less than 1 second, 0.81 seconds, which is an improvement still. The indexes that I created for this query were identical to the ones in the first example, searching for the kind ID and a range on production year for the title table, and on the cast info, looking up by role ID, and then although the movie ID wasn't part of the where clause, it was returned by the query, so it was useful to have that for the sake of a covering index. The explain showed me what it was doing. It did the same thing for the primary table, the title table, did a range scan because it was looking up a kind and a production year range. And then the dependent subquery was actually changed to an index subquery lookup, so it's actually able to scan the index only. It makes benefit of the covering index effect. But in spite of the fact that logically it should only have to execute that search for directors once, MySQL Optimizer seems to think that this is still a dependent subquery, which I believe is just a deficiency of the subquery handling in MySQL. I believe that this is improved in MySQL 5.6, but this test was run on MySQL 5.5. It just naively assumed that the subquery was a dependent subquery. However, the benefit when we actually get to execute this query and measure the handler performance is that only a fraction of the number of rows were actually accessed. It didn't have to run that query repeatedly, it seems. Measuring this in a different way than the explain output gives us a little bit better insight into what actually happens in this case. So this may also be a case where explain is giving us misleading information or incomplete information. The profile shows us, instead of executing the subquery many times and causing the information to overflow, it's actually showing us the status of the profile for all the initialization steps, the starting and so on, which indicates to me that it's not actually executing a correlated subquery despite what explain reported. It does execute the inner query. It returns data, but then there's also most of the time in this particular example is spent in a state of preparing, which actually I need to look into that a little bit further. I would think that preparing is actually something it would do earlier. In fact, you can see another line saying preparing a little bit higher, and I think this may be a mislabel as well. Another solution to the same problem would be to use an outer join. In this case, we don't have no subquery at all. The way that this works is I'm going to do a join between the title table and the cast info table, matching up the movie ID and looking for the rows in the cast info table for directors, role ID equals 8. I use an outer join because the way an outer join works is that if it finds no match, it'll still return the row from the first table, title, but it will just return all nulls for the columns of the cast info table. And I use the same where clause as I did before, the kind ID equals 1 and the range on production years. But then I also look for cases where the movie ID is null. If the outer join finds no match, and you know that it would have had to find a non-null movie ID if there were a match, because that's part of the condition in the on clause. then movie ID null must indicate that no row was found. That is, this movie found no matching row in cast info table to indicate a director, and therefore you get this exclusion join effect by simply doing an outer join instead of a subquery at all. And look at the stopwatch. It's lower still, 0.71 seconds. The indexes are the same as before, and the explain shows that we're getting a special optimization reported in the extra column for not exists. It's something that the left outer join can do to try to get that performance benefit. It's making use of the index in a covering index manner. The using index note refers to that. Counting the actual number of row requests is very similar to the previous example, but it was able to access them in a different way. And in this case, it shows what I would expect, that the majority of the time is actually copying the row data from one place to another, typically from the storage engine layer to the SQL layer, where it will be considered for joins and so on. So sending data, I often encounter people who think that sending data means that it's actually transmitting data over the network back to the application. But sending data in this context means it's moving data around in memory. That's the usual meaning of sending data. That is inside the MySQL server. So this is the summary of those three solutions that we saw for the exclusion join. The not exists, the best I could get, that was 1.20 seconds. That was the correlated subquery, very expensive. And the not in was better, and the outer join was better still. Your mileage may vary a little bit. You won't always see these proportions because your data is different than the data that I was testing with, and the number of rows can also, the data types of columns can affect the performance. So the point is, use all these measurement techniques to try to compare solutions. Don't assume that past results will indicate future performance. Another pattern is random selection. That is, we have a case where we want to pick a random movie from our database and display that. Maybe it's some sort of promotional feature or movie of the day kind of feature. The Naïve solution is to collect all the movies, order by the expression indicated by the rand function. So for every row comparison for the sorting, it would compare a random value to another random value and therefore sort them randomly. And once it's done all of that, then pick the first one that happens to be at the top of the randomly sorted list. So we use limit 1. This solution is documented widely. It's sort of a textbook solution. It's logically correct. It's simple to understand. It's even in the MySQL manual when they talk about ordering. The problem is it runs in a very slow performance. The larger your table, the worse it gets. Notice the stopwatch says 8.80 seconds. Even if I restrict the rows to just those that are movies using an index on the kind ID column, it will sort fewer rows than the entire table. It will exclude television shows and video games, but it's still going to do a lot of work. And the work is indicated by the explain. You can see the estimate of rows is almost 800,000 rows sorting, and it has to do that in a temporary table and sort it the hard way without the benefit of an index, even though it's used an index to try to limit its work only to those that are movies, the kind equals 1, it's still doing a lot of sorting. And you can see that also in the handler output, noticing how many rows are read, and you can see that even for this select query, which should just be reading, there's actually a lot of calls to handler write at the bottom of this list, indicating that it's populating a temporary table, writing those values into there, and then to sort it and deliver it to the result. In the profile, we can see the evidence of that too. The majority of time spent is in copying to temp table and sorting result. and that comprises a large majority of the time of the 8.8 seconds that we saw in the stopwatch. So that indicates the cost of doing it this way. Another solution, what if we could just pick a random value or a random position within the table and offset directly there and just read one row? That's another frequent solution that I see, and here's an example query that we could do that, or two queries. First, you need to know the count of how many rows there are of the matching type, where kind ID equals 1, and then multiply that by a random, so you can pick one between the first one and the last one in that count. Retain that value and then build it into a second query, which simply uses the random value as an offset into it. So no sorting at all, just offset a random number of rows into the set and return one that you find at that position. The stopwatch, notice I indicated it takes 0.0 seconds to 1.12 seconds. The variance is because the amount of time it takes depends on which random value is selected. If it happens to select one very close to the beginning of that list, a very low random value, it will find it very quickly. But if it happens to pick a random value close to the end of the table, it'll have to seek all the way through that and for that offset. So it's highly variable. Similar index on the kind ID as we had before. And the offset solution shows it's simply having to read a potentially high number of rows. The estimate here is sort of a worst-case scenario that Explain is showing you. It may have to search all the way to the end to find that. I did an example query where I simulated a random value which happened to be pretty high. I chose a 470,000, and therefore the status will actually show you it had to read through 470,000 rows in order to read past the offset plus count. The higher the random value, the worse it gets. But you could be lucky and you could get a low random value. The point is it's a highly variable performance. And likewise, as it is doing that, the seeking, it's actually returning the rows from the storage engine to the SQL layer, only to discard most of them except for the one that's returned by that limit 1. So that's where almost all the time is going, as you can see in the profile. A different method would be to find how many rows there are in the table, or you can alternatively use max ID in that expression. And then instead of using the offset of the limit, use the index. Use the random value that is chosen from the first query and use that as a range comparison to the primary key of the table to go directly to a position by index value rather than by row offset. And then I use a greater than because we may have chosen a random ID which isn't a movie. Maybe it's only, they happen to pick one that was a television show and we shouldn't return that. But in this case, we should return the next movie up in the sequence that actually matches the kind ID. I apologize, it looks like I forgot the condition for kind ID in the second query. So if anybody's already typing in a question about that, I recognize that there's a clause missing in the where of the second query. You should also identify kind ID equals 1 in the second query. In this case, it's using the primary key. It's using that random value to offset into the primary key by value rather than by position. The rows is also a worst case report. It says we may be reading that many. It's not taking into account that we're going to optimize that with limit to just read the first one found. So it's the potential is that it would read a lot of rows, but that's not actually the case. And in fact, the case when we look at the session status is that it does a read key, so it looks up by index value and reads one row and then finishes because there's a limit 1. So it actually just reads the one row. Also, the profile shows very good performance. Everything is taking less than 1,000th of a second, so it's quite speedy in this manner. And here's the comparison, the summary of these different solutions. We found that the Naïve solution with order by rand is so expensive. The offset is better, but still over a second, and the primary key looking up by value is much, much better. On the other hand, both of those latter two solutions require that you have the count, or at least the max ID from that table, and that can be another step that has its own performance issue. Depending on how frequently that table changes, how many new rows are added into it, you could cache that count. You could store that in a summary table or in memcached or some other in-memory cache, so you can reuse the value and don't have to do the count over again for every random selection. Okay, a new pattern, greatest per group. Say I want to find the last TV episode of every television series. And this, you can imagine that this would be very similar to the type of question that you may find in your applications. You know, finding the most recent event per user, or the highest scoring player per team, or any similar type of pattern. It takes many, many different variations, but it's always a similar type of problem that comes down to SQL. This is a lot of the solution that people may try to use, where they are looking for television episodes and they want to get the TV show title and the maximum episode number, which is easy to do if you use a group by. But then they also want to know the title of that last episode. Unfortunately, in this query, that the title reported is not the title of the last episode. In spite of the fact that we've done max episode number as last ep in this, it does not guarantee that the title will be the title corresponding to the row where that episode number was found. Why isn't it? It doesn't necessarily return the title from the same row where that value of the max episode number occurs. And as a comparison, I try to show people this query. What if we were to have a query that shows the episode title and then it has two more aggregate functions, the minimum episode number and the maximum episode number? Well, in this case, should the episode title be the first or the last episode? How should SQL infer what you want to be in that title? And likewise, what if we were to have other queries where we're calculating sum or count or average, where there actually is no row where the value occurs? What should it choose as the ambiguous column there? It turns out that this is an ambiguous query in SQL, and in most dialects of SQL, it's actually not permitted at all. It would be an error to do this. MySQL permits it unless you set a particular SQL mode to detect it and act like standard SQL. So how do we get that value? Here's one solution, exclusion join. That is, try to join to the episodes twice. Once to find the value we're looking for, and then the subsequent one, EP2, will try to find one that's one greater than that. And the idea is we're going to look for cases where EP1 is found, but EP2 is not because of the left outer join. And if there is no such episode with a greater episode number, then EP1 must have the greatest episode number. That's using the same exclusion join solution that we saw in the first query pattern, but this one does it in a different way to try to find the greatest per group. The key is to have multiple conditions in that join clause to find the same kind and the same TV show, and then also compare to see if we can find one with a greater episode number. And if we can't, then EP1 must have it. And then subsequently to that, join to the TV show as well if we want to find the TV show title. I created indexes to try to narrow down the kind ID for television shows, the TV show that it belongs to, that is episode of ID, and then the episode number for the range comparison. Unfortunately, this did seem to process a lot of rows. One of the tips about explain output is one way to estimate the number of row comparisons it's going to do for the join is to take the values in the rows column and just multiply them together. That works for joins, not necessarily for subqueries. So in this case, we have quite a high number of row comparisons because it's going to be multiplying 787,000 times the second value, 7,800. In spite of the fact that the second column is invoking a covering index, the using index, it's still going to be pretty expensive. So yeah, the read next ends up being a very high number and quite expensive in this case. I have seen this query solution be better, but it depends on how many rows you have per group and how many groups you have. So it can vary in different circumstances. This can be the best solution for certain data sets. And the majority of the time spent is simply copying rows around in the sending data state. Here's another way to solve the same problem, a derived table. This is a good use of a subquery. Instead of putting a subquery in the where clause, making it a correlated subquery, it actually puts the subquery in the from clause. So we're going to get a subs result from the table, just finding the maximum episode number and grouping by the TV show that it belongs to, the kind ID and the episode of ID. And that will be an interim result set for the derived table, the greatest episode number per show. And we join that to the episodes table again, comparing the kind ID, episode of ID, and episode number. So it naturally finds the row in EP that has that maximum episode number per TV show. And therefore, we can use EP to get the title, because it'll be the correct row. Notice that the time went down a great deal, down to less than a second. Same indexes, and much lower numbers that we see. It was able to reduce the order of magnitude of how many rows it had to scan in order to do that comparison. I did notice in the status that it was doing some handler writes. It was which usually corresponds to writing to a temporary table, even though explain didn't report it. Not only writing to that temporary table, but then the read R&D next indicates that it was reading through the rows of that temporary table in order to get it back. And we saw more evidence in the profile, where it showed us all the states of what it was doing, and then as it was closing up, it says removing temp table. So I think that it was creating a temp table as part of this, even though explain didn't tell us. So these are those two different solutions for the greatest per group. Again, test both of them, because it may change, your mileage may vary for your particular data set. Dynamic pivot. I want the count of movies, television shows, and video games per year in columns. Not like this. It would be quite easy to get the count per year and per kind if we were just to do a group by. But those would be coming out one count per row and one count and one production year per row, which is maybe not what we want for our particular report that we're generating. We would rather have, as the requirements for this particular task, to have the counts come out in columns, one column per year. The problem is pivot queries in SQL require that you know exactly how many distinct values you need to populate the columns for. You have to hard code the columns in the select list. You can't have the query automatically identify distinct values of years and create new columns as it finds them. You have to know which columns you have at the time you prepare the query, which is before it reads any of the values. So here's one solution. Try to if we know all the years, we can presume that we know how many distinct years we have. We can have an expression for each of the years already pre-populated into our select list. You may have to do a query against your table and find out the number of distinct years and use that to generate the second query. I'm using a trick here of MySQL, and that is if I want the count is equivalent to the sum of a bunch of ones. And think about that for a second. A count of how many rows of a particular condition is equivalent to the summation of ones where that condition occurs. And in MySQL, this is not standard SQL, but in MySQL, a Boolean expression will always return an integer 0 or 1. So in this case, I'm just comparing the production year to 2005, 2006, 2007, etc. And that's going to be a Boolean expression that returns either a 0 or a 1. The summation will not increment when there's a 0. It will increment when there's a 1. So it's a neat little trick. For that one-pass solution, I created this index on kind and production year so that we can get the correct grouping. And it tells me that it's doing an index scan, the type index for that primary table. It is creating a temporary table. And then the join to the title table is using an index, so it's able to get that pretty well. It did use a temporary table, and we can see that it's updating the counts in that temporary table for each of the 1.5 million rows that it finds. The handler right, the inserts to that temporary table are only 6, because there's only 6 distinct values in the data set that I was querying, but it updated, that is, incrementing the counts many, many times. And the majority of the time is spent building that temp table, and that's quite a bit of overhead there. The way I tried to improve this, one way, is to use the straight join optimization override. That is, I can now control which table is read first and which one is joined to it second. Straight join means use the order of the tables that I have in my from clause. Don't try to reorder them based on how the optimizer thinks that it can access them. Otherwise, the expressions are the same. And this does result in a better performance. Same indexes are used, but now no temporary table. It does a scan on the title table first. Before it had the title table second. And then every time it finds a title, it then looks up the kind ID using a primary key lookup, which is just fine. This is really the one pass. It doesn't create a temp table at all. It is able to scan through the table once in order and then get those counts. No temporary table. It's only moving rows around is the majority of time spent, but that's half of what it was before. And finally, I tested the Scalar subquery solution. This looks ugly. It looks like something you'd probably find somebody advising you not to do in SQL, that is to put a correlated subquery into the select list of a query. But the reason that this actually ends up being a win in this case is that there are very few kind types. There's only about half a dozen. So the outer query of this, the query on kind type K, is going to only return about 6 or 7 rows. And therefore it's only going to do that correlated subquery that many times. Created an index on the kind type table to look up that kind, and then on the for the correlated subquery, look up that kind ID and also take the production year so I can count it directly from the index instead of having to read the rows. And the explain looks a little scary because there's so many dependent subqueries. There's one for each of the distinct year values. But each one of them is using index, which is generally what we like to see as long as the indexes are fitting in memory. and there's no temporary table, there's no rights. It is making good use of indexes because these are all reading the next key value in order. It does show us a large number of dependent subqueries, so the length of this profile report I had to truncate for the sake of fitting it on the slide, but it nevertheless executes much faster. And you can see the orders of magnitude. The scalar subquery solution in this case for this data set was actually a tenth as fast as the best we could get with the joins. Again, your mileage may vary. Test all the different solutions, see what works with your data set. And relational division. What is relational division? I want to see movies with all three of the keywords espionage, nuclear bomb, and ejector seat. Movies have keywords that are associated with them. And some movies have quite a few keywords for all these different aspects or things that you may have seen in the movie. The solution that people often start with, and they get confused why it didn't give them the result that they wanted, is that they use the in predicate. Where here's an example where we're looking for titles that have the keyword in espionage, comma, nuclear bomb, comma, ejector seat. That is going to function differently than we expect it to. It's going to find movies with any of those three keywords because the in predicate is equivalent to saying where the keyword is espionage or the keyword is nuclear bomb or the keyword is ejector seat. We'd really rather it be more like and. The movie has a row in the keywords table for espionage, and it has a row for nuclear bomb, and it has a row for ejector seat. Here's the why that doesn't work with a simple where clause is that a principle of MySQL or SQL language in general is that the condition in a where clause has to reference one row at a time. That is, the expression there has to apply to one row. It can be the joined row from multiple tables, but it cannot consider items that exist on different rows than that are stored on elsewhere in the table. There is no row in this keyword table where the keyword value is three different values all at the same time. That's just it can't be the case that the column has a separate different values on the same row. We would like to see, as the result of this query, actually return to us the movie that has all three. So that turns out to be a single value. Single movie Goldfinger has all three of those keywords. The old 1960s James Bond film that has all three of those in it. One of the solutions is to use group by. That is, we look for keyword in espionage, nuclear bomb, and ejector seat like we did in the Naïve solution, but then we consolidate those with a group by so that they are all considered part of the same group, and then count how many distinct keywords were in there. So we'd want to find out if it had all three. We just see if when we match those three keywords, does the group have three rows? If it had only one of those, the count would be one. If it had just two of those keywords, the count would be two. The indexes for this would be to look up the keyword and then use the ID to match against the movies table, and then likewise the intersection table movie keyword would have a compound index to map between the two. Good range type is to look up the values in the keyword table, just because we're looking for three different values. That counts as a range. The intersection table MK does it using index, which is nice to do the mapping between them, and then a primary key lookup on the other side of that many-to-many relationship to find the title. That's the EQ ref is a primary key lookup. It did have to build a temporary table, but not with very many rows, so that's not so expensive. A temporary table that's small enough will fit in memory and not have to spool out to disk. Temporary tables are not necessarily prohibitive. They can be something that you can get away with if they are not too expensive, and if the data fits within memory, then that could be a good case. Yeah, most of the time here is spent building and tearing down the temp table, and yet the query was still overall, in absolute terms, pretty quick. The other solution for this is a self-join. It looks like a little bit more complicated query, but really what I'm doing here is just trying to work around the limitation that the where clause can only consider one row at a time. And I'm working within that paradigm by making sure that those 3 rows for the different keyword values are on the same row that's considered after the join has occurred. That is, I kind of concatenate them together horizontally so that I can apply a where expression against the whole set of them, and then compare using tuple comparison K1 keyword, K2 keyword, K3 keyword against those 3 values with an equal sign. You can do that. Many people don't realize you can compare tuples together in SQL. And look at the time. It goes down to 0.005 seconds for this. So in spite of it looking like a more complex query, it actually is able to use indexes quite well and get them back very quickly. The explain has more rows in it, but that's okay. Most of them say using index, so it's actually able to find the keywords quite quickly from indexes that are cached in memory. And then finally at the end of that, do a primary key lookup to the title. No temporary table. The updates and writes went away, and we were able to just do read key and read next, which are both index lookups and index scans to try to get good index usage. All of the values in the profile look very, very small. The biggest one is sending data, which is still only 4 milliseconds. So here's the comparison of those 2 different solutions. I've scaled it up to a millisecond, so it's 100 milliseconds versus 5 milliseconds. The self-join solution is 20 times faster. So conclusions and wrapping up. We have multiple tools that we can use to measure query performance and give us insight in different ways. Explain, session status, and query profiler. And we saw cases of in each of those different query patterns where one gave us the crucial information that we needed to understand where the performance was really going. Another important thing is test with real-world data. If you test with a trivial amount of data, just insert 10 rows into a test database, you may not get the right results. The optimizer will actually tell you something different about using a tiny table than it would against a table that's large. So if you can use a copy of your production data to do the testing for profiling queries, that's best. And also tuning is very important to make sure that you have enough memory on your server so that the indexes are going to stay resident in the buffer pool in RAM and gain the performance improvement that way rather than be swapping out and having to be reread from disk. That can kill your performance. I'd like to remind you that I work for the training department at Percona. We have many classes offered in the US and Europe and around the world. You can go to percona.com/training and find out what our offerings are and our schedule for training class near you. And I also wanted to mention that I wrote a book a couple of years ago, SQL Anti-Patterns, Avoiding the Pitfalls of Database Programming. I had a good time writing that book based on my experiences of answering questions online, the MySQL forums and Stack Overflow and places like that. So you can check that out. And also keep in mind that Percona puts on events each year. The next one is going to be in London in November, but there's also one in Santa Clara, California in the US. So you can come and visit us and see the good presentations and speeches by the leading MySQL experts to find best practices and all the new technology that is emerging to see what's going on. Percona.com/live. And that's the end of my presentation. So, Elisa, do we have questions to fill in the last few minutes?
Hi, Bill. Actually, yes, we have several questions, so I'll go ahead and read them to you. And if we don't get to all your questions, I will make sure that Bill gets a copy of them, and he will address anything that was not answered in a follow-up blog post on MySQL Performance blog. And with that said, I will jump into the first question. Can you compare the use of subqueries, multiple joins, versus multiple queries, e.g. temp tables?
Well, as we saw, there's different ways to use subqueries. There's some subqueries that are dependent subqueries that have to execute many times. And there's some other cases where subqueries just execute once. And there's derived tables, which are subqueries. And we also saw subqueries in the select list, so correlated subqueries that are scalar subqueries that you can return. Many different ways you can use subqueries. Some of them cause temporary tables. Some of them execute in different ways. My only general statement is that there are so many variations there that you really have to do further analysis. You can't come up with a one-size-fits-all rule for when to use a subquery and when to use joins. We even saw cases in my presentation where some of the join solutions were much worse than the equivalent subquery solution.
Okay, next question. Why doesn't the query optimizer take care of the execution decisions? Since they are all logically the same, I believe it should translate to the same execution plan. And he writes, I know it doesn't, though.
Right. The query optimizer has limits to it. There's cases where it can infer what you mean and infer that there's a logical equivalence to two different queries of different forms, but constructive grammar is complex. You can always come up with a SQL statement that is more complex than the cases that the engineers who have designed the query optimizer have accounted for. So they've done a pretty good job. In MySQL 5.6, they've actually improved the query optimizer quite a bit, and you can try out your tests there. But it's still sort of finite in its complexity. There are cases that it still doesn't understand how to optimize. So there is some work that you have to do as a developer and to understand the logical meanings and how that matches to practical reality to try to assist the optimizer by creating the correct indexes and possibly overriding the optimizer with index hints.
Okay, next question. Doesn't the primary key solution for random selection only work when the IDs for movies are distributed uniformly over the range? And he wrote down 1 ... max ID.
Indeed, using the range of looking up the primary key does have a risk of giving artificially choosing IDs with a greater frequency if there's a gap preceding that. So if you had, say, a whole bunch of contiguous IDs and your random value is hopefully randomly distributed over the whole range, and then there's a gap between your IDs and then a whole bunch of more movies, but there's 1,000 missing values in between. Any of those randomly selected values within that gap of 1,000 would all map to the next movie that's following the gap, presuming the random number is generated evenly. So yes, you do have a risk that entries following gaps like that are chosen more frequently, and that just has to be a compromise position for your case. The workaround for that would be if you were to actually give a separate ranking ID to all the rows in your table that are guaranteed to be contiguous. So aside from the primary key, you might have another value in the same table, and you just populate that with numbers that are known to be contiguous, and then you can choose a random value and be assured that you won't miss any. You can use equality rather than greater than in that case. But it depends on how strict your randomness needs to be.
Okay, and we have time for one more question, and I would remind everybody else that we will answer those that weren't answered in the blog. So on the dynamic pivot, the straight join, can you explain more about why you thought about doing that and why it helped?
Sure. The straight join was necessary because if I allowed the optimizer to just choose the entries, it automatically reordered the tables in spite of the fact that of the order that I put them into the query. It decided that it was advantageous to reorder them for some heuristic rule that is built into the optimizer. Maybe it preferred to look up the kind ID first because it wanted to look it up by primary key, and it has some rule in the optimizer that says that primary key lookups are better for some reason, or another reason. Using the straight join allowed me to control that and to tell the optimizer, don't try to be clever here. In this particular case, you're going to do the wrong thing, and I want to reorder. I want you to access these tables in the order that I give them to you. So there are some odd cases where the optimizer may choose the wrong order, but those are really the exception rather than the rule.
Okay, well, thank you so much for your time today, Bill. And audience, I appreciate your attending our presentation today. Like I said, I will send out a link to the recording within 48 hours, and Bill will answer any questions that were not answered in a blog post on the MySQL Performance blog. With that said, I'd like to wish everybody a happy weekend, and we hope to see you back on another webinar sometime in the near future. Thanks again, Bill.
Thanks, Alyssa.